Good morning to everyone. So am I audible to you?
Good morning, sir.
Yes.
Good morning.
Yes. Okay. So let us start today's class. So before enter into the today's session, let's see recap what we studied in the previous class. So in the previous class, actually we took an example as design methodology, that is top design, top to bottom and bottom to top design methodology. So in this we took the example as that one of the example is ripple 4-bit ripple carry counter. We seen the program how it is. This is the program which it shows here. It is a 4-bit ripple carry counter using gate level model. As you know how to write this program, we explained already. Second thing is we are having the instance. This is the ripple carry. It's nothing but your top module. Remember, this is your top module of the program. When you run this program, the system will ask. So it doesn't find the module name as TFF anywhere else because each and every component the TFF is there. So you need to write a separate instance program for that. So the TFF program. So now again the TFF program is written using the gate level modeling. The T flip-flop is derived from the D flip-flop. So we need two components to build a T flip-flop. The one is a D flip-flop, another one is NOT gate. This also we seen in the previous class. So next, so here you see, if you run this program also, again it may ask it not able to find the DFF the instance actually, because the NOT is a primitive. The Verilog has the inbuilt primitive NOT actually. So it doesn't have any problem, but a DFF. So another one more problem you have to write DFF flip-flop. That is a D flip-flop program with a synchronous reset. You see, because it is a counter as asynchronous counter, it is not a synchronous counter. So asynchronous counter in the sense the D flip-flop in the diagram you can see the inputs are these are the inputs and the outputs. So here the always at cross edge reset or neg edge reset. If it is a synchronous reset, only the changes what will have. The change will be if it is a reset. If it is a synchronous, in the sense we have only neg edge clock, we won't have the cross edge reset. Remember, if it is a synchronous means, if it is asynchronous, then we need this. So for synchronous, let me write this is. For synchronous, just I'm going to write only that line. This line only I'm going to write. This one. Always at neg edge clock. Only this will come, then other lines and will come like this. Yes. So we have. You may think there is no begin here. Why the begin is not written? You asked. The system as considered as here, it is like the if statement, the complete if statement here, it is a single actually because if else. So it is considered a single statement. That is the reason here they not used begin end actually. Even though if you use begin end, it is not an issue. I hope this is clear. So this is for synchronous. This is for synchronous reset. This is for here it is given asynchronous reset. Like this only we have to write. Is it clear? Do you have any doubt in this? The difference here is we have to do the reset here only during the negative edge in the synchronous reset. But in the asynchronous reset, you can do the reset either in the negative edge or in the positive edge. So anywhere. So that is the reason here is given. Positive edge reset is given here. Because of in the statement if we return as reset. If reset means by default, what is the meaning of that? The meaning is reset is equal to 1. That is the meaning of that, right? So this if reset means what? Reset is equal to 1. That is the reason we written here positive. If it is a negative reset, then here we have to write neg reset. Now next you can see how we can say the illegal instantiation examples like nested module. As we know, we cannot nest the model, nested model in the sense one model cannot be written within a model. Within a model, we cannot write the one more module because you can see this is the module. In Verilog program, any Verilog program, once the module starts, then we must need a n module. Between the module and the n module, we should not write this. See, the another module, the n module should not come. So this is wrong. That is the reason we can say it is illegal define. So it is illegal to define the module TFF inside this module. Like you may think, because the ripple carry counter only has T flip-flop. So the top module name I may give as a ripple carry counter. Inside this program only I'll write a separate T flip-flop program. You may think no, it is wrong. So you need to write separately. So if you are writing the 4-bit ripple carry counter now, how many total programs are required now? Programs required. How many programs are required? Any answer? First program, which is one is 4-bit ripple carry counter. So I will name it as ripple carry counter rcc.b. File name. This is a file name. Second, what I will do? TFF. That is T flip flop. So I will name it as TFF.b. T flip flop because that is second program. Which is third program? DFF. That is D flip flop, right? At D flip flop. I will name it as like this DFF.b. Third program. What is the fourth program now? R. That is fourth program is S-bench program. So the program name I will name it as RCC underscore test dot B. See, if you want to run and if you want to test this 4-bit ripple carry counter program, then we must to write, you must to have these many files. 4 files you should have. So then only you will get the output. So the fourth is satisfied for test bench actually. So these 3 are must. When you are going to run, even any one is missing, your ripple carry counter will not run. Because it may run, it won't give proper output. Is it clear? I hope you understood this. See, now we are showing that stimulus test bench style here. Stimulus test bench style, you can see this is the stimulus block instantiate the design block. The sense which is your design block, your top level module, that is nothing but ripple carry counter. This only. This is your design block for which program you are going to write. Then entire thing, this box only I can call, this is what nothing but a stimulus block. Which one? This block. This empty block only I can call the stimulus block. Stimulus block means what? Already as I said. What is the meaning of stimulus block? What is the meaning of stimulus block? Stimulus. Insert the stimulus. If I say insert stimulus means what? Insert the values with the delays after the initial begin. That only is called a stimulus block. See here, we'll have the stimulus block. We'll force from externally the clock value on the reset value. Based on that, I'll get the Q. Now, if you see the stimulus and the design block instantiated, like the internal view of this. This is the diagram which shows the internal view. See, like here, top level block. Which is our top level block? Your top level block is nothing but RCC. Carry counter is nothing but your top level block. Then this will be your stimulus block. This is the stimulus block. You can see in the normal D flip flop, just there we have clock. Here this is a dummy variable we created. D underscore clock, D underscore reset, C underscore Q. That should be mapped with your ripple carry counter because this is your stimulus block. Okay, so now each and every input variable and output variables are mapped. Already we written in the test bench code. You might have remember. So how we return? Say example in the sense I can say like this: RCC ripple carry counter. Then RCC1 is an instantiation. Then what are the input for ripple carry counter? That is nothing but I can say clock, comma, then reset, comma, Q. See, this is nothing but you will write in your test bench program. You will write like this only. After the module test, then wire register. After that, it will come like this. So that is the reason here. So as I said earlier, it is not mandatory. You have to use the same name only. You can use the different name also. That is the reason here. You can see clock reset Q in the ripple carry, but the stimulus clock in the test bench they use D underscore clock, D underscore reset, C underscore Q. Then this variable name doesn't matter actually. Only the matter is here. We need to map it properly. The order we can check. The order must be proper. This variable names are you can give any X, Y, Z, no problem. But the order should not change. That is very important. Even if you want to change the order, for that some other method is there that we'll study in later. Even you can change the order also. That we'll study in the later. Now you see here, this is the simulation. After the simulation, you will get like this only. This is the clock which is generated. The clock period is generated here. How much in the sense? Like the clock, one clock is 10 nanosecond. So one clock is 10 nanosecond in the sense, what is the meaning of that? What is the meaning of the one clock is 10 nanosecond means it is nothing but the positive is 5 nanosecond, the negative cycle is 5 nanosecond, then totally I'll get us 10 nanosecond. That is why. So I can say this only. See this timings. So this will be 10. Then this is a reset. So as per our diagram, then your counter will start to count when reset is 1 or when reset is 0. When the counter will start to count. Any answer? The answer is in front of you only. In the screen only the answer is there. Any answer?
Sir, 0.
0. Reset is equal to 0. Why is 0? The initial diagram, you can see that in the initial diagram, in that we drawn in the clock, there was a bubble. I think you might have noted that. That is, your counter will work in negative edge. Means reset negative edge it will work. At the same time, we given in the program, you might have seen in the previous program the D flip flop. When the D flip flop was working, that is very, very important. You can see here. Just see here. When reset is 1, the Q is 0. See? Correct? When reset is 1, the Q is 0. When reset is 0, then only the Q follows the D. So I can say when you are getting the data, when reset is equal to 0 only. So then only your counter will start to count. So that is the reason here. When reset is equal to 0, then counter is starting. See? The counter is starting 0. Next 1, 2, 3, 4. Keep on. It will go. Once it reaches the 15, again 0, 1, 2, it's coming over there. But you can see here what happened. During at this time, there was a asset. There was a asset in the reset. It's become 1. When the resets become 1, what will happen? So we'll get counter will be reset to 0. That is why it's happened here. So let us write how to write the test bench program for this. We need to see. So before showing this, let me write a simple program, then we'll get a clear idea. So I will write the program for test bench program for D flip flop, or let me write the program for T flip flop. I'll write. It will be very easy, better. So test bench program for T flip-flop. Okay, let me write test bench program for T flip-flop now. So as we know what is the logic of T flip-flop, I'm not going to write the T flip-flop program. What is the test bench for, what is the truth table for T flip-flop? What is the operation of T flip-flop? What is the operation of T flip-flop? Yes? Do you people, can you hear me? See, T flip-flop.
Toggle.
There is T. Then here I will give clock. Then I will give one reset. Then this will be Q. Example. Okay. What is the truth table now? Clock, reset, clock. Sorry, clock already is over. T, then Q. So we are going to work in the rising edge of the clock. Now you tell me, I am going to make a reset. When reset is 1, okay? When reset is 1, so I'm going to make T is equal to 0. What is my Q? Q will be 0 because I'm going to reset the flip-flop. Correct? So reset is 1, Q is 0. Now again, what I'm going to do, so again you see, reset is 1, still the reset is 1, T is 1. What I'll get? What is Q? Q is still is 0 only due to reset is 1. Reset is 1, Q is 0 only. Now, reset is 0. When the reset is 0, now I'm going to make T is equal to 0. What I'll get? When reset is equal to 0, so T is 0. If T is 0, Q is previous value. What is the previous value? The previous value is 0. So the same 0 will get maintained. Next, reset is 0. T is 1 now. When the T is 1, what will happen? Automatically it will go enter into the toggle condition. So what is the previous value is 0. The new value becomes 1. Now reset is 0. Now again T value is 1. What will happen? Still T is 1 in the sense, again will be toggling only. So the previous value is 1, again we get 0. Next, still the reset is 0, T is 1. What will get? The previous value is 0, it becomes 1. Again reset is 0, T is 0 now. Let me make T is 0. What will happen? It's maintain the previous value. The previous value Q is 1, so it remained 1 only. Now if I make reset is 1, if I give reset is 1, what is the T value? T value I'll give don't care. Nothing but what? Irrespective of anything, whether 0 or 1, I'll get Q is 0. This is what the truth table like this only will get. So now we are going to write the test bench program for this. Now let me write program module TF of underscore test. Next, wires, from this only you can say wires are nothing but outputs, inputs are registers. So wire Q, then reg T, clock, reset. Next, now we have to instantiate. So our name is, I call it TFF. TFF, T underscore FF 0. See, TFF 0, that is label. Then order I'll say same. The order is T comma clock comma reset under Q. That's the one. Now let me write initialize. Initial. Next, begin. First, what you'll do? Initial clock is equal to 0. 1 dash B 0 will make. Second, we should give some reset. We have to make reset, right? So reset is equal to 1 dash B 1. Reset. So when reset is 1, it's going to reset your flip-flop. That is reset is equal to 1, then it will be 0. Now, what you will do next? Now you think I should not write like this. After 5, the clock is equal to 1 dash B 0. Then hash 5 clock is equal to 1 dash B1. So because as you know, the clock value will get turned to 0, 1. See, already 0 is initialized, 1. Then you may think you should not write like this. It is wrong. See, this one is wrong. We should not write like this. So you may think now what I should do if it is wrong in the sense, right? So for that only what I will do here, before only or last, I will say last, how to write that clock. Now leave me the clock. Still what I should write, I should make T, initialization not done, T also. Initialize T is equal to initialize 1 dash B 0. Okay, 3 inputs. Now what I will do, let me write now. Clock, leave the clock, later I will write. First, after some delay, that is after hash 10, the reset goes 0. Now what happened? Your flip-flop starts to conduct. Reset 0 means at the same time what I'm going to make, till keep T is equal to, let it be that, because still I'm going to maintain T is equal to 0 only. Now after 10, I'm going to make T is equal to 1 dash P 1. T is equal to 1. Now the very important thing in the T flip-flop, you need to see that toggling condition. Correct? So what I need, I don't want to change the reset now. Why? Because when keep on reset is 0, then only flip-flop will work. So now what I'm doing now, I'm going to make some long interval like hash 100. I'm going to change T is equal to 1 dash B 0. What is the meaning of this now? After 10, not after 10. This is, you see from here, this is wrong. You see this, don't count this counter, you come from here. 10, 20 plus 100, 120. You can see after 20, the T becomes 1. After 20. From 20 to 120 plus 100, right? From 20 to 120, that is a period of 100, T will become as 1. Will be long time. So automatically what will happen? You will get toggle condition. At the time only T goes 0. Now what I will do again, hash 10, that is delay 10, reset I'm going to make as 1. Now what I will do, end. Now you may think still, where is the clock? You may think what I will write, I will write here. Clock, the one more thing I'm going to start. The new thing is called as always. Always, it is a single, right? Always hash 5, that is delay 5. Delay 5, clock is equal to negotiation of clock actually. Now for meaning is what? We initialized here, the clock is 0. We initialized already. Correct? We initialized already clock. We initialize already clock, right? 0. Now automatically what will happen? See, we initialize the clock is 0 in the sense, hash 5 in the sense, then automatically after 5, the clock will become not of clock. 0 will become 1. So from 0 to 5, it is first 0 to 5. 0 to 5, it is 0. Then 5 to 10, after again 5. Like this. So I can say this period of this. This one. This period is how much now? This period is 10 because this is 5, this is 5. So for every 5 screen time units, the clock will get invert. So I will get like this. My clock will become as like this. For every 5, the clock will become as 101010. It's like this only it will go. That is the reason we have to use always. Very important thing. The always is not a finite, it's a infinite. It won't complete until you will give the stop. Okay, it will keep on, it will run up to indefinite time actually. But when you use the initial begin end, so it will run up to the last, how much the delay is given. Up to there only it will run. You can see, but when you use always, it continuously it will run with the infinite time. So now I need to stop that. How can I stop? Further, one simple idea is there in the Verilog. Simple here. What I will do, hash $100. It's a one of the special function in the Verilog. Dollar finish. If I give like this, automatically what will happen? What is the simulation time from this? You can say no. Any idea? What is simulation time now? Can I get any answers for this? What is the simulation time?
230.
230. 10, 10, 20, 120, 130 plus 100, 230. So 230 nanosecond. Yes. This is the simulation time. It will get stopped because even though here always is there, because of this dollar finish, so it will get stopped actually. If I'm not used to this, automatically then what will happen? It will go indefinite. That only the clock will run. The other things will be stopped. It won't run. It will be maintain the previous value only. So now we need to see how we'll get the waveform for this. So as you know, you got it right. So now very simple. I can say this is the simple clock. So how the waveform will be? Now the clock will be like this. This is the clock actually. This is the clock. Next reset. Okay, we need to make a reset. First reset is 0. You can see reset 10. In the sense, you assume the clock period first. This is 5. Total clock period is 10. You assume like this. This total is 10 actually. You have to assume in this way only. Each pulse is 5. Like this only think. Okay, see. This is the 1 clock cycles. What are the line I'm drawing here? This is for 1 clock cycles. Okay. Now next is I'm going to draw the reset. Now you can see reset. First we initialize the reset, right? Here already we initialized. So next we have to draw the reset. Initially reset is 1. The reset is 1 up to what? 10. After 10 reset goes to 0. Up to 10 reset is 1 only. So reset is high. See? Reset. This is reset. Then reset goes low. This reset is 0 low up to when it's getting changing. So here 0. When it's just change 1 actually after how many? 10, 20, 120, 130. After 130 means 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120. See example, just you consider somewhere is 130 here somewhere. Okay. Here then reset goes. So just you think like this, just dot dot dot. I'm thinking here the time I'm getting as 130 here. Here is 130. Okay. So now next is this will be your reset. Yes, next. What is next is T. T initially is 0. When it's got 1. So same. T is 0 here. See? T is 0. Next is goes to 1. Same like this you think. T is going to 1 until which time? After 10, T is become 110. After 110. After 110 means I can think, you may think like this here. That is 130 means this is 110. This is 130, 120, 110. I'll make here only. Until here, T is 1. Next, it will become as 0. This is T. Now you can see based on the Q I will get. So it will get stopped. This is what the waveform will generate in a system. So now the same thing only we are going to show in the ripple curry counter.